Okay, so yeah, let's jump in. So I'm part of CQC2T, which I assume most people are familiar with, but it's an Australian Research Council Center of Excellence. These are the 7 universities that are a part of it. Within Australia, we also have over 20 international partners, and it's a rather big coordinated research center. Check out the website if you want to know more. My group is called Kermit. It's pronounced Kermit. The QU is for, I don't know, quantum, whatever. It's like quantum RMIT, but we pronounce it Kermit. So you can check that out as well. I want to start with a cautionary tale. And this goes all the way back to my PhD, which I did. Complicated story, not that complicated, but I went to Princeton to do string theory. After a year, decided I didn't want to do string theory. And I got an offer to work with Mike Nielsen at UQ. Andrew was there at the time, a few other people. And so, yes, Dominic was as well, that's right. And so I spent 3 years at UQ as part of a 5-year Princeton PhD, which was a really nice thing to do because Brisbane is better than New Jersey. Anyway, one thing that I was asked to look at by Jared Milburn, so I was working with Michael and with Jared, which was great, was he suggested I look at correlations in this paper. So not in the paper itself, and the idea behind the paper. So trapped ion simulations of quantum fields in an expanding universe. And the basic idea of this paper, John Dowling's on the paper. That's why I'm bringing it up. So the basic idea is you have ions that are in a linear trap. They're arranged vaguely like this, and there's an overall electric potential that's provided by some end caps that keep the ions confined. There's also confinement that keeps them in a line. But the basic idea is you can change this potential by changing the voltage. You can open it up, and when you do, the ions will move apart, and that's sort of like an expanding universe, right? Okay, so that's the idea, and that's what this paper proposed. And so Jared said, well, let's look at correlations in this system, and maybe we can get some freezing out like they have with inflation and some interesting ideas. Okay, good idea. So problem was I didn't really understand the physics of the system. I was a new PhD student. I didn't really get what was going on. I was reading it many times. I kind of got the maths, but I just had some questions. But I figured I could do the maths without worrying about this. And there are certain people that I've worked with who have this same philosophy, Giacomo. And so this is meant to be a cautionary tale because I gave the worst talk of my life ever at Caltech in front of Jeff Kimball and John Preskill. And I'm very glad to be here today because this was a real worry for me. I was terribly embarrassed. It was the worst talk because I didn't know what I was talking about. I thought I knew what I was talking about, but I didn't actually know what I was talking about. And those two asked me questions about the actual physics of the real system that revealed that I didn't really know what I was talking about. Ions, yes. And also how the ions related to the physical system. Because I mean, we're doing an analog here. So, you need to know both. So I decided, so after this, I was very embarrassed. I went back to first principles and I discovered the paper was totally wrong. This paper is wrong. It's very wrong. The reason is that canonical momentum is not equal to mechanical momentum in general. Now, how many people know what the difference is between canonical and mechanical momentum? Ooh, not even half. Go learn it. Lagrangian mechanics. I know we do Hamiltonians. I know we start with Hamiltonians. Don't start with Hamiltonians. Start with the Lagrangian. Understand what is canonical about the canonical momentum. It's actually a Lagrangian partial derivative with respect to the velocity, the generalized velocity. It is not m times v, and it is not gamma mv. That's the mechanical momentum. And if you believe that these are the same, which they often are, you're going to make mistakes when you have things that change. So in accelerating frame, this is all different. So at Milburn Fest in 2018, John was up there, and he said he was talking about this paper and how great it was, and I just said, yeah, but it's totally wrong. And then again, I felt embarrassed because like it was like, well, what are you doing? Why are you shitting on this guy? But I figured it's John, so I can do that. Afterwards, we had a discussion, and he told me that the original calculation used one ion, and he just thought, whatever, it'll be easy to generalize to multiple ions. No, it's not. It's a totally different physical system. The basic reason is as you expand the trap, the ions actually start to move and they heat up way more than they would in an expanding universe, which is a different physical phenomenon. Anyway, the lesson is always understand the physics of the system. Don't assume the maths is fine on its own or that someone else is taking care of it. Other authors eventually pointed out the problems in that paper, which is good. However, my awful talk at Caltech led to a successful collaboration with a PhD student there. He just saw through all the awfulness and said, there's still something cool here, let's do it. It wasn't on trapped ions, but we published this in 2009, just the two of us. And then Jared and I published 2 papers on trapped ion simulations, one with a single ion. And then we worked with Jay Olson, who was one of John's former students as well, on the actual way to simulate quantum effects of cosmological expansion using what turns out to be a static ion trap, believe it or not. You just change the energy levels. You don't actually expand the trap. So this was, anyway, that's a long arc, but I thought I'd add that. So I'm going to transition back. That was the aside. That was the John connection. I want to talk about CV quantum computing. So most people are familiar with qubits here. Some people will be familiar with CVs, but the basic idea for quantum computation is that you want to be able to do anything that's physically possible to your qubits. If you have a single qubit, you want to rotate it in the Bloch sphere. Now, with CVs, the notion of CV quantum computation has the same general definition. We want to be able to implement any unitary that we can on a continuous variable mode or modes. And a simple example of one would be a displacement like this. So it just shifts the wave function over. But the basic idea is that for quantum computation for any dimensional system, you have however many of these things that you want, and with a minimal set of gates or procedures. Did I do that? Okay. So with a minimal set of gates, you can construct whatever operation you want on those physical systems. All right, so that's just the background. We're going to work with wave functions, not with qubits in what I do. Okay, so why bother with CV systems? So I'll bring this up just for some background. So at the practical end, Terry may have comments on this, or he may be working on other things. That's totally fine as well. But you know, we have different approaches. PsiQuantum is going full bore with the single photon qubit-based optics. Xanadu, who I consult with, is working on the CV approach. At the practical level in optics, we have deterministic entanglement for CVs. It's immensely scalable, has been demonstrated in laboratories at Tokyo and Denmark and Virginia, and Xanadu, and room temperature operation for much of the computation. For all of it, if you want to do photon counting, but it turns out you don't need to do much photon counting. In circuit QED, microwave cavities are less noisy than the transmons. So that's kind of nice because the cavity is a CV system. Transmon's a qubit. And so if you reverse the roles, instead of the microwave cavity being a bus or an ancilla, if you make that the primary system, you can actually do better. At the fundamental level, you avoid premature optimization. For instance, in optics, why should we restrict to photonic qubits? That's just some wave function. We've just chosen that for what reason? I mean, there may be better choices. There's also more options for practical tasks. There's quantum cryptography, cluster states, and there are hybrid schemes in use CV methods to implement manipulate photonic quantum states. Disadvantages, imperfect due to finite energy, and we eventually need to discretize for error correction. So we're going to have to put qubits in there somehow. At the fundamental level, there's more questions to answer. For instance, what discretization are we going to use? I just said you don't necessarily want to use single photons. Well, which one are we going to use? Okay, well, hang on, we'll figure it out. That's a big question. And you have to incorporate the effects of noise from day one. This is complicated, but it's easy to end up writing a crap paper if you don't talk about the noise at all, if you just assume that everything can be ideal. Because ideal is actually unphysical when it comes to continuous variable. A position eigenstate of an oscillator is not a physical state, but it's the limit of a bunch of physical states of smaller and smaller variance. Okay, both together. You have to do extra work to employ existing algorithms. There's a smaller literature, fewer optimized experimental platforms. So these are some of the advantages and disadvantages, not meant to be an exhaustive list, but this is what we have, and this is why I work on CVs. Okay, but I want to talk about, in this talk, encoding a qubit into a mode. So 2001, Gottesman, Kitaev, and Preskill came up with an encoding for qubits that looks basically like this, although this is the physical version, not the ideal version. So this is a wave function. This is not a mode-locked laser. It is not a frequency comb. It is a single mode for which we're plotting a wave function. So if you look at just the blue, this is the zero wave function, the logical zero wave function in a single mode. Q is a plus a dagger, roughly, over root 2, really. But anyway, we move on. The one state is this superposition of peaks. And remember, it's single mode. So what you actually have, if you just had one peak, this would be the wave function for a squeeze state. If you had two peaks, like the one at 0 and the one at 2 root pi, you would have a cat state, slightly not perfectly symmetric cat state, but that's what it would be. This is a squeezed cat state. This is a squeezed multi-cat state, which I learned in Japanese is squeezado maruchi neko jotai. Anyway, neko is cat, jotai is state, and squeezado is squeezed. And maruchi is multi. Okay, anyway, so the GKP state has the property that when you displace, so the ideal one has these being infinitely thin, so they're delta functions, and they go on forever. So it's a Dirac comb. And so you take a Dirac comb, you shift it by half a period, and then you shift it again, you're back to the same comb. And that's like the X gate. So you go from 0 to 1, back to 0. And that's what they've done. The nice thing about a Dirac comb is that its Fourier transform is also a Dirac comb. So when you do momentum shifts, you do a Z gate, and then it comes back to itself. All right, so this was their code. But what happens when you use this in physical architecture, here's the CV cluster state, you're going to teleport it down. What you see is that you start with, yeah, this works. Okay, good. So you start with this one, which is an unequal superposition of 0 and 1 with no relative phase. And then over time, it degrades. With each step of the with each teleportation step, it degrades until you get down here, and it's not very useful. So what we do is we stop it somewhere in the middle, and we attach it to an ancilla state of the an ancilla GKP state, and we can do error correction on it. Now, some of you may have noticed that my circuit is going right to left. Hopefully, you noticed that. You may have also noticed that the measurement is just a bra. I'll get to this in a second. Just be aware. But what this circuit does is it actually cleans up this state. So you have finer spikes than were there. They're fatter before, and now they're finer. But it's a little bit offset. And the outcome tells you the offset. Or rather, it tells you the offset mod root pi. It doesn't tell you which way to move it back. And in fact, that's the problem. You have to guess which way to move it back so that it's on the grid. If you move it back correctly, which happens with some probability, depending on the original noise, then you have no error. And if you move it back incorrectly, then you have a logical qubit error. By logical, I just mean at the qubit level, you have an error. And so that's fine. We know how to deal with qubit level errors. We can do quantum error correction. Great. So this is a way of discretizing the errors. Yeah. Yes. No. But all of the noise that accumulates is tolerable. You can, big question, but you can deal with it. So an ideal homodyne measurement, which is what this is very close to what is done physically. If you wanted to make it physical, you could actually put a squeeze state. You could also put a POVM that is a very narrow sum of a bunch of projectors centered around the outcome that you want. It's all fine. All of that works. Good question. Okay, brief aside, right to left circuits. Sometimes it's called the Kitaev convention. I decided I'm going to go full bore on this today. So here's the circuit that I started with. So what the hell's going on here? Why is he complicating things? You might be saying to yourself. We have left to right. It's what we've done since, for 20 years now. Nielsen already settled this. Why is he doing this? Well, the answers are it's easier to learn, especially for new students. This is what I found experimentally in my own group. Visual connection to calculations and representational simplicity. I'll show you what I mean. So let's start with this circuit. Can you move that pointer out of the way, please? So let's start with this circuit and let's generalize it a bit. So rather than any particular state as an input, just some general pure state chi. Ins on the right, outs on the top. Top wire is what we're looking at. The outcome is, so we're doing a P measurement indicated by the P basis with outcome S. All right. So I'm going to give it some room, and I'm going to look at what's in this box. What's in this box is some Krauss operator. because it is something that takes an input state and it gives an output state and it signals an outcome. So it is a member of a well, anyway, it's an outcome dependent operation. It's not unitary, but it is but it does preserve purity. So this is what's in the box. Depends on chi, like I said, and it depends on the outcome. You can control chi, but you can't control the outcome. Okay, well, how do we work with this? And why is right to left so good? Why am I going on about this? Well, measurements are just bras. So this is quite nice because, well, you'll see why. But measurements are just bras. So if you're worried about like, well, how do I do this in LaTeX and the Q circuit and all that, you can do it in Q circuit. If you want to know, ask Blaney or ask Giacomo or ask me, and then I'll tell you to ask them. And it's actually quite easy to get it to go right to left. But you don't need the measurement icon. You just use this. You just say, what are you measuring? Also, if you want, we can put some gates in here. So we have a Z dagger acting on the bra of P0, and that makes a PS state. We can turn in the Q basis like this. We don't need to do this, but I'm just illustrating it because if you want to combine gates in the right to left form, guess what happens? There's no reversal. Do you know how complicated this is for new students to deal with? Like if your students are able to deal with the fact that when you're going right to left and you put two boxes together, you have to reverse what's inside, then they're not using that brain power for things that matter. And if you have students who struggle a little bit, this is going to help them out a lot because that is amazing. It's only amazing because we use a stupid convention where we don't have this. You take two boxes, you put them together, and you got to mess with what's inside. That's ridiculous. So I like this a lot better. Yeah. Yeah. It's not post-selection. It is the measurement outcome. I'll show you. So this is what happens. So we're actually calculating this Krauss operator, and we get some outcome S. That's what comes out here as a classical outcome. You do a measurement in the P basis, and you get some outcome S. Okay, and that's represented by bra, P basis. Because you do not have to reverse anything. This is the physical one. This is the physical measurement that you're doing. You're doing a physical P measurement. And I am decomposing this with gates. That's all I'm doing. I just have a bra there in my circuit. I just have a bra. You know, see, this is the thing. Like the fact that you're asking questions means that this is not intuitive. But if once you get to this, you're like, oh, why wasn't I doing this the whole time? Because once you have this, cat, yes, then what you can do is you can say this whole thing is a Krauss operator. Well, how do I evaluate it? Well, you just drop the wires. Okay. No, I'm serious. You don't have to think about it. You don't have to figure, oh, what do I do? How do I rearrange it? You just drop the wires. So that's our Krauss operator. Well, what does that mean? Well, then we just turn the boxes into hats. I like hats. Again, it's good for the students to know that this is an operator. You can't just move it past. And we just replace the gates with what they are. So if there's a wire up there that's missing, it's just identity tensor that. I use vertical tensor products to indicate this. It's all very visual. And then if you want to do it that way, fine. You can rotate it around and then you evaluate it. It turns out it's this. It's the momentum space wave function evaluated at the Q operator. If you want to know what the hell this is, it's very cool. I'll talk to you about it later. But that's my pitch for right to left, why I think we should do it. It's in papers, no problem. There it is. So measurements are just bras, gates combined without reversal. You can extract Krauss operators, almost no work with this, and students appreciate it. Well, you can ask my students, but I think they do. All right, end of the aside. So let's go back to GKP. All right, why bother with GKP? Well, this you may want to take a photo of if you have any interest in optics. But basically to do quantum computing with qubits, well, quantum computing in general, you need 1 and 2 system Clifford gates. You need something non-Clifford. You need to prepare and you need to measure. Oh, I'm sorry. You shouldn't take a photo of this one. Let me just jump ahead. Take a photo of that one. Take a photo of that one. All right. Well, I'll get to that one, but don't take a photo yet. I'm sorry I said that. Because for photonic qubits, the advantage is that all single system operations are just passive. You just have beam splitters, you have phase shifts. For photonic qubits, dual rail qubits, it's all passive. For 2 system Cliffords, there's some post-selection involved in the usual KLM style way of doing it. Any kind of interaction with measurements is going to be post-selected unless you're doing something clever. preparation, you can do it. Kind of tough. Measurement's pretty easy. For general CV, the analog of Clifford is Gaussian, and the analog of non-Clifford is non-Gaussian. Okay. For GKP, which is an encoding of a qubit into a CV mode, look at the connection here. All of the Clifford gates are Gaussian, and that's really nice because what it means is that you can do all of your qubit level error correction, which is a lot of the circuit, with just Gaussian operations, and that's a big advantage. And in cluster states, all this can be done, CV cluster states, all this can be done at room temperature, so that's also a big advantage. The non-Clifford gate is currently non-Gaussian in this slide, and making the state is terrible, but the measurement is easy as well. It's all homodyne. In 2019, we took a shot at this and found that you can actually do this with Gaussian operation as well. So this was the big result. And then the next year, Takaya, Matsura, where are you? Takaya and collaborators showed that you can actually go the other way. If you start with magic states, you can make the other states, the eigenstates. But anyway, the point is here, look, all this is Gaussian, homodyne, as long as you have the states. So that's a nice conceptual advantage and a practical advantage. All right, so if you want this slide, I'll send it to you. GKP states have been made in trapped ions. This is what their Wigner function looks like. They've also been made in superconducting circuits, but they have not been made in optics. Okay, I'm gonna have to go quickly through this. So back to this. Let's look at this state to begin with. The problem, GKP has some conceptual issues. For one, the definition differs from how it's used. It's defined as a comb, but you never actually have a comb. And you're going to get outcomes that are not exact multiples of root pi. So we just deal with that. We just say if it's closer to an even multiple than an odd multiple, we treat that as a 0. Okay, so the ideal GKP logical subspace is entirely unphysical. We bin measurements of Q and P to get the qubit level Z or X outcomes. And also, large displacements by even multiples of root pi, which should do nothing, end up giving an actually orthogonal state. So that's a little bit strange. So how does the particular shape of the wave function affect the logical content? That's what we want to know. How do we deal with this? Well, we would like a code that reflects how these states are actually used in practice. We'd like an actual logical qubit, and we like to rigorously capture the parts of the state that don't matter logically. For instance, tiny displacements or overall large shifts by 2n root pi. And we like to account for any logical qubit noise due to state imperfections. So that's what we want. In 2020, Giacomo and Ben and I came up with this, which we call the modular bosonic subsystem codes. Basically, what we do is we take the real line, which is we take the Hilbert space for a CV mode in the position representation. And we collect the eigenstates of position, which I told you aren't physical, but they're close enough. Just work with me here. And we bin them. We logically collect them into bins. And then we say, well, we can take all these blue bins and just shove them together like dominoes. You just move them together. And then we take the red ones, take them out, move them together. And now you have 2 copies of the real line because infinity. And so now you have a direct sum of 2 copies of the real line, which is a qubit tensor of the real line. And so what you have is a logical qubit based on modular position tensor the remaining information. So what we do is we take the position operator and we write it as root pi times some integer operator, which tells you which bin you're in, plus some offset within the bin. So this is limited to between 0 and 1, or scaled, really. And then we take the parity of m and call that the logical qubit value, 0 or 1. And then we have some gauge operator as well. So there's a gauge mode here. The details here you can check out in the paper. But conceptually, what happens is this. We have a wave function, and we highlight the areas that surround the even parts. And we say our decomposed state is a 0 logical state tensor this wave function, which I'll show you in a second, plus a 1 logical state tensor this wave function. And that's, you can write any wave function like that. You can always say it's 0 tensor something plus 1 tensor something. That is entirely general. It's not a Schmidt decomposition, but it is a valid decomposition. You can always do it for any wave function. And so that's what we have. So in our gauge mode, we have an entanglement between the logical qubit and the gauge mode. So we have 0 tensor this wave function plus 1 tensor this wave function. That's the modular bosonic subsystem decomposition of that wave function. Okay, so in this picture, the gauge mode states are slightly different. So now, okay, hang on. So if you look at the peak here, this actually has a single peak at the middle, and then two peaks that are lower on the side. This wave function does not. It has two peaks that are the same height, so they're slightly different. So that means that this two system is slightly entangled. So there's an entanglement between the logical qubit and the gauge mode. This creates decoherence of the logical qubit. So the fact that the wave function is not ideal is represented as decoherence. All the standard tools of quantum information are now available. And this is a non-Markovian model because the gauge mode, the bath, still sticks around and re-interacts with the logical qubit as the total state evolves under natural or noise or a gate operation. Okay, so we have an approximate state. Yeah, right, I'll do it. So what we have is, for high quality states, dephasing is the dominant logical noise. The axis of dephasing, the z-axis, depends on the choice of position for our subsystem decomposition. You could play the same game that I just described using the momentum representation instead, and what you would see is a different effect. You would have a different subsystem decomposition, and you would have slightly different noise here. So if you decompose with P, it would dephase about X. And so what we have here is if you look at A, what you have is a bunch of high quality spikes, very wide envelope on the state. You can do that. And that represents a very high quality plus state. Now, as the, oh, that's the wrong button. It didn't do anything. Okay, fine. So as you damp the spike heights at the ends, you get slight dephasing. Because now, depending on which spike you get, it tells you a little bit about, well, anyway, I won't go into the explanation because I'm gonna misspeak it. But if you keep going, what you find is that it actually travels up here until once you just have a single spike, you no longer have a plus state anymore. You actually have an encoded zero state. So these are wave functions for which we have done the subsystem decomposition, as I just described, and then just traced out the gauge mode. And this is the logical state that you get in the blocks. Okay, so let's see what that looks like. So beyond GKP, logical equivalences. So I'm gonna illustrate some. So position eigenstate, centered at 0. This decomposes. It only has support in the blue, and the gauge mode is the same between the two because there's only one. This is the 0 logical state tensor, a position eigenstate in the gauge mode. Okay, so that's nice. So this is another way to represent a 0 logical state. It doesn't have any error correction power in momentum, but it does in position. Okay, a 0 momentum eigenstate is an equal superposition of all position states. And this has the same wave function in the blue as it does in the pink. So it's actually a logical plus state with a momentum eigenstate in the gauge mode. That's kind of cool. A 0 GKP state looks like this, and it turns out it is a 0 logical tensor, a plus GKP in the gauge mode. And in fact, that's true for the 1 as well, and it's true for any GKP state. So the psi, for whatever state you have encoded in GKP, is just that state in the logical qubit tensor, a plus state in the gauge mode, plus GKP state in the gauge mode. That's just the little dictionary that we have. That's what I showed here. What's cool about this is that if you take the gauge trace of the position eigenstate represented as a density operator, you get the same as the gauge trace of the GKP 0 state represented as a density operator. And it's just a logical 0. So what can we do with this? This is kind of like, what's going on here? Same with the plus. Interestingly, this solves the problem of the large displacements, because if you displace by a big amount, then what you see is that the logical content is still the same. Okay. So in my consulting role with Xanadu in 2020 and 2021, we came up with this blueprint. And one aspect of this blueprint, yeah, thanks. One aspect of the blueprint is that it is, I'm going to make a note of that. One aspect of the blueprint is that we're making a Rausendorf 3D cluster state, where the reds are GKP states. We want it to be GKP everywhere, but the generation of GKP that's been proposed is non-deterministic. So we're coming back to some of the same problems that with photonic qubits, which is non-deterministic generation of the starting states. But what we found is that we can maintain the connectivity in this cluster state by swapping out a momentum squeeze state for a GKP state, because it has, and this was the insight that I had. This idea came about from several different people. My suggestion for this, which is not the only person suggesting it, but my reason for suggesting it was the logical equivalence of the zero momentum state and the plus GKP state. And it turns out this provides some significant advantages to the architecture. So that was one nice conceptual benefit that we got out of it. Applications, we had 3 applications. This is work with Giacomo, these 2. And then this is some of my work with Ulrich Anderson's group. And I'm going to talk about this one briefly, hidden qubit cluster states. So the question I want to answer is CV cluster states and GKP. Why do they play so nicely together? What's going on there? I'm aware of the time. I'm going to just put up a dictionary. I'm going to do this visually, so you don't need to know what's really going on here. But what I'm going to say is that in a cluster state diagram, we have a graph. We start with plus states for qubits, zero momentum states for CV modes, or plus GKP for GKP states. And what we're going to do is in the subsystem decomposition, we're going to decompose that into a logical qubit, which is represented by a diamond, and a circle and a square, which together make up the gauge mode. You don't need to know the difference between them, but it has to do with the bin number and the position within the bin. But visually, this is what we have. And so if we do a controlled Z gate between them, then this is the entanglement structure that results. And what I want you to notice is, if you just look at the diamonds, you have a 2-qubit cluster state, but it's entangled with a bunch of other crap, which represents the entanglement with the gauge mode. But also notice it is only entangled with its neighboring gauge modes. Okay, fine. A plus GKP state looks almost the same, but instead of an equal superposition over all of the modular variable, it's actually just a single spike in there. Okay, so that looks like that. And so if you have this, just like if you put a 0 state in place of a plus state with a cluster state, you actually disconnect it. Or in other words, if you measure a cluster state on a Z basis, you disconnect it. Similarly, if you have an empty circle in this picture, it disconnects all the connections to the other pieces. So all you're left with is this qubit level cluster state at the logical level. So that's why GKP states are very good qubit cluster states. So going back to this is what a CV cluster state looks like, which is fully Gaussian. And the GKP one looks like that. Okay, you can see that it's embedded in there. Okay, so that's what we have. We also have hybrid versions that look like this. And if you have an arbitrary state, you can put it in there like this. This is, you can see it a little bit more generally here. You can kind of see what's happening. If it's fully GKP, you just have your qubit level logical cluster state, and then the gauge mode is entirely disentangled. It's a separable state between the gauge modes and the logical cluster state that you have embedded there. So this is the final thing I want to get to. Unzipping CV cluster states with GKP. So CV cluster states comprise a logical qubit cluster state entangled with neighboring gauge modes. Each teleportation step measures the physical mode in momentum. So that's what's happening here. We're going to measure the physical mode in momentum, and we're going to teleport it down the line with a Fourier transform. That's what happens. And so going back, measuring the momentum actually measures all of these in a way that I don't have time to describe, but I can do it visually. So all right, so what does it look like in the subsystem decomposition? So we're going to take these 3 measurements, and it turns out that a momentum measurement is actually separable among these 3 subsystems. The bin number, the position within the bin, and the qubit. Turns out you're measuring in the plus minus basis for the qubit, and you're measuring in appropriate bases for the other 2. And so because there are 3 local measurements, even though it's within full mode, you can actually do the 3 individually. So let's do this one first. Well, let me finish. I'm not saying you're physically doing them separately, but I'm saying that logically what's happening can be done in any order. So let's just do the middle one first. We can delete that. It's not a physical thing to do without messing with the others, but you can still do it at the mathematical level. I'm aware I'm eating into my question time. I just need another minute. You can do it at the mathematical level. You just do that one first. That does nothing because it's not connected. This one is where it's interesting because we can derive a rule that just like when you have a plus state and you teleport it in a cluster state 1 unit, it undergoes a Hadamard and becomes a 0. If you do that, it actually blows up the entanglement and it disconnects the entanglement with any other modes that it touches. And that's illustrated here by teleporting into this and destroying the entanglement. So by measuring this one, we teleport in something that just blows up the entanglement. So now we've done 2 out of the 3 physical pieces of the physical measurement. Teleporting the filled square injects an open circle, which is a modular position eigenstate, into the neighboring system's circle system. This disconnects all links involving the circle. And so measuring the gauge mode of a GKP state unzips the CV cluster state. And now look what you're left with. You're just left with a logical level connection of cluster state connection. And so now the final measurement, which is part of the physical one, just teleports as it would. Okay, so that's the reason why GKP plays so nicely, as illustrated by the subsystem decomposition. So some observations. Decomposing in Q versus P biases the logical noise to Z versus X. That's a choice. It introduces bias noise. In practice, we would measure P for logical X, so dephasing may be fictitious in practice. Some of Andrew's work I'll get to. Cosine wave binning, square wave binning, which is used in optics. Our code respects this in Z, but not in X. There's a different type of binning, which is used in circuit QED to extract the logical block vector, dephases along all axes, and it's like the X behavior in our code. GKP's original gauge set acts non-trivially on the gauge mode, unless it's an ideal state. And other simpler states have the same logical content as GKP. What's the significance of this? That's an open question. And of course, there is also this paper by Mackenzie Shaw, Andrew Doherty, and Arnie Grimsmo, which appeared in the last couple months. It's symmetric with respect to X and Z. There's no preferred dephasing axis. It acts in both Q and P as our code acts in Q. And so that's a nice advantage. It's faithful to ideal GKP error correction using these binned homodime measurements, although I realize that the term binned homodime may be the wrong term. Anyway, another possible code should exist that acts in both Q and P as our code acts in P, which is an unforgiving type. It would be faithful to logical GKP state reconstruction used in circuit QED and trapped ions. So I'm going to leave the conclusion slide up there. Thank you.
Thank you, Nick. We maybe have time for 1 or 2 questions.
So you had your blue and red columns.
Yes.
Basically split them up and then put it back together. Do I need to read that as like the new wave function that is continuous along the word?
Oh, I see. Yeah.
So then my actual question is when you have your coherence, you start to see like a bit of an overall Gaussian.
Yeah.
Go up.
Uh-huh.
So you get discontinuities.
You get discontinuities, yeah.
Yeah. So is that going to
It doesn't matter in practice.
okay.
No, it's fine. Talk about it later. Maybe get to one more question. Let's do that. Any others? I thought about that. Well, I mean, you know, like this, I don't know, is the short answer. It's an interesting idea. You could go all the way down. Yes, you could take the bins and further bin them and then further bin those and then further bin those. And in fact, you don't even have gauge mode anywhere anymore. You just have bins. You could do that. We haven't looked at that, but it's a fascinating approach.